Hi everyone, in this lecture we are going to be discussing the force terms. So as we know, this is a force term ut into F into the thickness into dA. This is the body force term. So we know that U is given by U and V since this is a two-dimensional body. Okay, also F can be represented by Fx and Fy. So when we multiply ut into F, it is u v Fx Fy, and we will get u into Fx plus v into Fy. We also know that u for a CST, so we have a CST with nodes 1, 2, 3, and these are the degrees of freedom: Q1, Q2, Q3, Q4, Q5 and Q6. So U is given by N1 into Q1 plus N2 into Q3 plus N3 into Q5, only the displacements in the x direction, and V is given by the displacements in the y direction. So when we substitute all this in this equation, we will get, and T we are taking it as constant over the element, so let us represent it by TE. Into Fy integral E N1 dA plus Q3 into TE Fx integral N2 dA plus Q4 TE Fy integral N2 dA plus Q5 integral TE into Fx integral N3 dA and Q6 TE Fy integral N3 dA. From this diagram, which is to the left, we know that some integral N1 dA, this represents the volume of a tetrahedron whose base is AE. So this is the tetrahedron and the base is AE, and height of corner is equal to 1, that is this height, and this is given by 1/3 of AE. Similarly, integral N2 dA will be 1/3 AE. So the volume of the tetrahedron is given by 1/3 into base area into height. So the base area is AE and the height is 1. And integral N3 dA is also equal to 1/3 of AE. So substituting in the above equation, we get integral ut f into t dA equals to q transpose into f e. Okay, that is Fe is the element body force vector, and it is given by Te into Ae upon 3 Fx Fy Fx Fy Fx Fy transpose. So these element nodal forces contribute to the global load vector, which is denoted by F, and the connectivity of the elements needs to be established. So from the connectivity table we can get the global load vector F by adding up all the element body force vectors Fe. In the same way, if there is a traction force, so this was for the body force, now let us talk about traction force. It is a distributed load which is acting on the surface of the body, and such a force acts on edges connecting boundary nodes. So a traction force acting on the edge of an element also contributes to the global load vector, which is this. The contribution can be determined by considering the traction force term, which is given by integral U transpose T into the thickness into dl. Okay, so now let us consider an edge with nodes 1 and 2, and the length of this is L12. It is acted upon by a traction force. Okay, it's acted upon by a traction force Tx and Ty, and the unit is force per unit area. So this is Ty, and Tx is what is marked in blue. This is Tx. Now we know that U is given by its components in x and y direction. Similarly, T also will have components in x and y direction. So using this integral length over the length 1 to, we get Utx plus V Ty dl. Using the interpolation relations and the shape functions, we know that this is only for the length L1 to so here this is Tx1, this is Tx2, and this is Ty1, and this is Ty2. this is the component distribution. The normal pressure of this surface will look something like this. So this is the actual traction force, and this is when we split it into its components in x and y direction. So this face is inclined at an angle of theta to the x-axis. Now the integral of n1 square dl is given by 1/3. Similarly, we have n2 square dl, which is again 1/3 of L12, and integral over length 1 to n1 n2 dl is equal to 1 by 6 into L12. Now looking at this diagram here, we know that this has the coordinates x1 y1 and node 2 has the coordinates x2 y2. If we need to find out the length of 1 2, okay, it will be under root of x1 minus x2 the whole square plus y2 minus y1 the whole square. If we want to get cos of theta, it will be y2 minus y1 upon the length of 1 2. Similarly, sin theta will be given as x1 minus x2 upon length of the member 1 2. Next, the traction force in the x direction at node 1 is given by minus c into P1, okay, where this is P1 pressure at node 1 and P2 is the pressure at node 2. Tx2 is given by minus c into P2. Ty1 is given by minus s into P1 and Ty2 is minus s into P2. Now substituting in the equation, these values, we will get Q1, Q2, Q3, Q4 into the traction force of the element. Okay, so Te is given by the thickness of the element into the length upon 6 2tx1 plus tx2 2y1 plus Ty2 Tx1 plus 2 Tx2 and Ty1 plus 2 Ty2 transpose. So this formula will be used to solve problems which are two-dimensional plates and subjected to traction forces. So in this lecture we have covered up how to use the body force term and the traction force term and how they will add up to the global load vector F. Thank you.